You have used the phrase light year your whole life. In an argument, in a documentary, in a sentence you finished without hesitating. You have never once stopped to ask whether you actually feel the size of what you just said. And there is a precise, testable reason you haven't, sitting underneath the word like a foundation nobody inspects. Here is the plain fact first, because it deserves to arrive before anything else does. A light year is a distance, not a duration, and it is exact. 9 trillion, 460 billion, 730 million, 472,580.8 kilometres. It is what you get when you take the speed of light, fixed by international agreement since 1983, with no error bar left in it at all, and let it run for one full orbital year. It is not the smallest such unit, and it is not the only one. Light crosses a much shorter gap in a second, a longer one in a minute, a longer one still in an hour, and professional astronomers mostly skip the light year altogether in favour of something called a parsec. All of that is true, and none of it matters yet. What matters is the one number above, and what it is going to do to you over the next 2 hours. Hold on to that family for a moment, because it is going to matter later. A light second, a light minute, and a light hour are all honest, working units, used constantly by people who track spacecraft and planets, and none of them will give you any trouble tonight. The trouble starts at exactly one specific point on that ladder, and figuring out precisely where the ladder stops behaving is most of what these 2 hours are actually about. So here is the answer to tonight's question, stated plainly. Before you have any reason to trust it, no, you cannot comprehend a light year. Not with more effort, not with a better analogy, not by being smarter than the last person who tried. The reason is not a mystery, and it is not a personal failing. It is a specific, measured property of how your brain represents size, and it has a name, and you are about to watch it happen to you. Live in less time than it takes to boil water. Try this. Picture, for 1 second each, 4 amounts of money: $1,000, $1 million, $1 billion, $1 trillion. Do this properly, rather than skimming past it, because the whole rest of the night depends on you actually noticing what happens in the next few seconds, rather than simply agreeing with the description of it afterward. 1,000 feels like something. A used car, a nice month. 1 million feels bigger, comfortably bigger, the kind of number that changes a life. Now notice what happens to the next 2. 1 billion is 1,000 times the million you just pictured. 1 trillion is 1,000 times that. Again, if your sense of size were tracking the actual arithmetic, $1 trillion should feel to $1 million roughly the way 1 million feels to $38. An almost unimaginable gulf. It does not feel that way. For nearly everyone, billion and trillion sit in the same rough neighborhood in the mind, both absurdly rich, both more than anyone needs, separated by an adjustment so small it barely registers as a difference in kind at all. That gap between the arithmetic and the feeling is not a flaw in you specifically. It is a documented property of human cognition, and it has been measured directly on exactly this range of numbers. In 2013, 3 cognitive scientists, David Landy, Noah Silbert, and Alea Goldin, asked ordinary American adults to place numbers between 1 and 1 trillion on a blank line, one end marked 1, the other marked 1 trillion. A little under half of the people tested placed the numbers correctly, spread out in proportion to their true size. Almost everyone else did something specific and strange. They treated 1,000, million, billion, and trillion as though those 4 words were an evenly spaced list, like the rungs of a ladder, and put 1 million roughly halfway between 1,000 and 1 billion, nowhere near where it actually belongs, which is a sliver's width from the 1,000 end of that line. The digits were right there in the words. The felt size of the digits was not This is where a light year lives, and it is worse there than it was a moment ago in your bank account, because at least $1 billion is a number you have watched build, coin by coin, in a life you can imagine living. 9,460,000,000,000 kilometers has no such foothold anywhere. It is not simply a bigger version of a number you already know how to feel. It is a number sitting well past the point where feeling stops scaling at all, in the company of every other quantity this large that a human being has ever tried to hold. The count of stars in a galaxy, the number of seconds in an age of the Earth, the population of a planet, and it is about to get harder before it gets easier, because the sky itself is unhelpful in a very specific way. Your eyes give you depth by comparing two slightly different images, one from each eye, and that trick only works out to a range of a few dozen meters, enough to judge a thrown ball or a step on a staircase, and nothing more. Past that range, your brain switches to a different set of tricks entirely. The way haze softens a distant hill, the way a nearer object blocks part of a farther one, the way things closer to you slide past the background faster when you turn your head. None of those tricks reach the stars either, so every star arrives on what is effectively a single flat surface, at no felt distance from any other star, no matter what the numbers underneath them say. The instrument you are using to look at the problem cannot report the very quantity the problem is about, which means every method left available to you tonight has to work without the one sense that would ordinarily do this job for free. None of this is despair, and none of it is an excuse to stop trying. Over the next 2 hours, we are going to try, seriously, using every method a careful person has ever reached for. Familiar comparisons, physical scale models, the conversion of space into travel time, and finally the real instruments that professional astronomers actually use to measure these distances for a living. Some of what follows will feel, for a moment, like it is working. Watch closely when it does. That feeling is the most interesting data point of the entire night, and by the end, you will know exactly what it is made of, and exactly what a light year was actually built to do, which, it turns out, was never quite what you assumed. There is a specific name for the failure you just watched happen in your own head with that money. And by the time your pulse has ticked over a few dozen more beats, you'll have it. The same quiet count your body has been keeping since before you could read a clock. Running now, whether you're paying attention to it or not. The name comes from a 19th century German physiologist, and it did not start with money or with stars. It started with weights on a scale, in a lab in Leipzig, with a man named Ernst Weber asking a much smaller question. How much does something have to change before a person can tell? Hold that question for a moment, because the answer to it turns out to explain everything from the money you just imagined to the ladder rungs. Landy, Silbert, and Golden found people using, to the reason 1 trillion kilometers and 1 billion kilometers can sit, unfairly, in the same drawer of your mind. Weber discovered that the smallest detectable change in a weight was never a fixed amount. It was a fixed proportion. Hold 100 grams and you'll notice about 2 more grams added. Hold a kilogram and it takes 20 grams before you notice anything at all. His colleague, Gustav Fechner, turned that observation into a law in 1860, and the shape it produces is the same shape you just watched operate on your own idea of money. Perceived size grows by ratios, not by amounts. Multiply a stimulus by 10, and the felt increase is roughly constant, regardless of where you started. That is not a rule about weights. It is a rule about the machinery, and the machinery does not know or care whether the number in front of it is a kilogram, a dollar, or a kilometer. Neither Weber nor Fechner had any interest in astronomy, and neither of them ever wrote a sentence about starlight. That is worth sitting with for a moment, because it means the mechanism about to be described was not invented to explain tonight's problem. It was discovered independently, in a completely unrelated corner of 19th century science, decades before anyone thought to ask whether the same limit might apply to the distance between stars. which makes it a considerably stronger kind of evidence than a theory built specifically to justify the conclusion it reaches. Put the two findings side by side, 90 years apart, from two completely different fields, and they say the same thing in two different vocabularies. Fechner found the compression in a physiology lab on people holding actual weights in their actual hands. Landy, Silbert, and Goldin found the identical compression in adults who had never touched a gram of anything, just looking at the words million and billion printed on a page. The compression was never really about weight or money or distance. It is about magnitude itself, in whatever costume it happens to be wearing. And a light year is wearing the heaviest costume available. So that is the shape of tonight. Honestly stated before we begin. Not 6 tricks that will each promise to fix this and then fail one after another for no clear reason, but one real, sourced, structural limit, tested fairly against every method people have actually used to get around it. Comparison, scale, time, and instruments built by professionals who have spent careers on exactly this problem. Nothing about that structure is a trick played on you. Every method gets a genuine, good faith attempt on its own terms before the night moves to the next one. Because a limit that only survives by refusing to be tested honestly would not be much of a limit at all, and it would not be worth 2 hours of your night to describe one. Some of those methods are going to feel, for a moment, like they are succeeding. Pay attention to what they actually deliver when that happens, because the gap between the feeling of success and the fact of it is where the real answer to tonight's title is hiding. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Before any of tonight's numbers could exist, one thing had to be settled first. And it was not obvious at all. That light takes time to get anywhere. In the 1670s, the working assumption among most astronomers was the opposite. That light simply appeared everywhere in the same instant it left its source. Nothing in ordinary experience argued against it. Strike a match, and the room brightens without any perceptible delay. If light did travel at a finite speed, that speed would have to be so enormous that no earthly measurement could ever hope to catch it in the act. A Danish assistant at the Paris Observatory disagreed, and he had 5 years of notebooks to back it up. His name was Ole Rømer, and the object he had been watching was not a star but a moon. Io, the innermost of the 4 large satellites of Jupiter, discovered by Galileo in 1610. Io slips behind Jupiter and back out again, on a cycle of a little over 42 hours, regular enough that 17th century astronomers had begun using it as a kind of interplanetary clock. Predict an eclipse of Io, observe it from 2 different cities, and you had a way to compare local time across an ocean, which was exactly the tool navigators needed to work out longitude at sea. The stakes were not academic. A ship's captain in the 17th century could determine latitude easily enough, from the height of the sun or the pole star, but longitude, position east or west, had no comparably simple method, and the absence had already cost fleets dearly, wrecked on coastlines their navigators believed were still days away. A reliable clock in the sky, visible from anywhere, checkable against a known table of predictions, was one of the most valuable practical problems in the science of the age, and it was the reason careful astronomers across Europe were timing Io's eclipses at all. There was a problem with the clock. It drifted, and it drifted in a pattern nobody could explain by adjusting Io's orbit alone. When Earth was moving away from Jupiter in its own orbit, the eclipses arrived a little later than predicted. When Earth swung back toward Jupiter, they arrived a little early. The error was small, at most a matter of minutes, but it was consistent, and it tracked Earth's position rather than anything happening at Jupiter. Rømer's explanation was that nothing was wrong with Io at all. What was arriving late, when Earth was far away, was not the eclipse. Light needed time to cross the extra distance, and that extra time was the entire discrepancy. The The room full of skeptics deserves a fair hearing here, because their position was not foolish. Nothing in daily experience suggests light needs time to arrive anywhere. A candle lit in a dark room seems to brighten the walls instantly, with no perceptible lag at all, and an assumption built on that kind of evidence, repeated every single day of a person's life, is not easily overturned by one assistant's notebook full of eclipse timings. He did not simply publish the idea and hope. On 22 August 1676, the Paris Observatory's director, Giovanni Domenico Cassini, told the Academy of Sciences that light seemed to take somewhere between 10 and 11 minutes to cross half the width of Earth's orbit, an observation Cassini himself later backed away from. Rumour pushed the claim further and made it fall or stand. He predicted, in advance, that the eclipse of Io due on 9 November 1676 would occur roughly 10 minutes behind the schedule every previous method would have produced. It happened almost exactly as he said it would. On 21 November 1676, Römer read an account of the result to the Academy in Paris. It survives as a short, dry record. No flourish, no triumphant flourish about a new constant of nature. Just the claim that the timing of Io's eclipses could not be explained unless light took a measurable amount of time to travel. Römer estimated that light needed about 22 minutes to cross the full diameter of Earth's orbit. The modern figure is closer to 16 and a half. He was off by close to a third, working with a pendulum clock, a none too steady telescope, and a moon 300 million kilometres away at its nearest. And he was still right about the one thing that mattered, which was that the number was not 0. Cassini was never convinced. He remained a public skeptic of Römer's interpretation for the rest of his career, even as better observations kept confirming it. What Römer had actually done, whether the room in Paris understood it that night or not, was open a door between two ideas that had never needed to touch before. Distance had always been a question you answered by comparing lengths. Duration had always been a separate question, answered by comparing durations. The moment light was shown to move at a fixed, finite rate, the two stopped being separate, because once you know exactly how far something travels in a given time, either quantity can be rewritten in terms of the other. Nobody in that room reached for that consequence in 1676. It would take another century and 3/4 before anyone did. The number itself did not stay rumours for long. Better tools kept arriving. Rotating mirrors in the 19th century, radio timing in the 20th, lasers bounced deliberately off reflectors that Apollo astronauts left standing on the moon. Each method narrowed the figure further, until, by the middle of the 20th century, the speed of light was known to a precision that outstripped the metal bar, then used to define the meter itself. In 1983, the arrangement was flipped. Rather than measuring the speed of light against a fixed length, the world standards bodies fixed the speed of light, 299,792,458 meters per second exactly, and redefined the meter as whatever distance light covers in a corresponding fraction of a second. The speed of light stopped being a measurement with an uncertainty attached to it. It became the ruler other things get measured against. That is the number behind everything you heard in the first 2 minutes tonight. Multiply it by 1 full year, using the fixed convention astronomers actually use for that year, 365 and a quarter days, so that the same figure comes out no matter who does the multiplication or when. And you get the exact distance named earlier, down to the decimal. Every digit in it is there because two people, one in the 1670s and one at a conference table in 1983, insisted on precision in a place where the culture around them had been content to guess. None of that made the number any easier to feel. It only made it exact. Go back to the compression from the opening. The one that flattened $1 trillion into roughly the same emotional neighborhood as $1 billion. Because it deserves more than a demonstration. It deserves an explanation. And the explanation turns out to be older than psychology as a formal discipline. In the 1830s, a German physiologist named Ernst Weber was investigating something that sounds almost too simple to publish. How much heavier does a weight have to become before a person holding it notices the change? He found that the answer was never a fixed number of grams. It was a fixed proportion of whatever was already being held. Someone holding 100 grams could detect an added 2 grams or so, a 2% change. Someone holding a kilogram needed roughly 20 grams added before noticing anything. Again, about 2%, even though 20 grams is 10 times the earlier threshold. The nervous system, it turned out, was not counting grams. His colleague Gustav Fechner spent the next quarter century turning that single observation into a general law, publishing it formally in 1860. The consequence, worked all the way through, is that perceived intensity grows in proportion to the logarithm of physical intensity, which is a precise way of saying that equal ratios feel like equal steps, while equal differences do not feel equal at all unless they happen to sit at the small end of the scale. Double a quiet sound and you get a noticeable jump. Double an already loud sound by the same physical amount and you barely notice, because doubling represents a much smaller ratio once the baseline is already large. It is worth pausing on the specific numbers, because they are more concrete than compression makes them sound. A 2% threshold means that doubling a small weight is enormously noticeable, while doubling an already large weight requires adding a further 100% on top just to register the same subjective jump, which is precisely why lifting a second identical suitcase feels dramatic, and lifting a 50th identical suitcase, if such a thing were possible, would feel almost like lifting nothing new at all. The rule is not vague. It has a specific mathematical shape, and that shape is the same one that governs every other example in this chapter. This is not a quirk confined to weights held in a laboratory. It shows up wherever a physical range is enormous, and a nervous system has to compress it down to something usable. Sound intensity is measured in decibels for exactly this reason, a scale built, on purpose, as a logarithm of physical energy. Because the ear's own response to loudness already behaves that way, and an engineer trying to describe a whisper and a jet engine on the same linear ruler would need a number with 11 zeros in it just to talk about the jet engine politely. Light does the identical thing to your own eyes, every single day, without you ever noticing the machinery at work. Step out of a dark room into full midday sun, and the physical intensity of the light striking your retina can increase by a factor of many thousands within a second, and yet the sensation you report is not many thousand times brighter. It is closer to very bright, registered on roughly the same short emotional scale you'd use for a bright lamp. Your visual system is compressing that jump the moment it happens, using cells and chemistry rather than a screw-adjusted lens, for the same underlying reason Weber found in a hand holding a weight. A nervous system built to operate across an enormous dynamic range has no use for a linear report of it. It needs ratios, not amounts. And it has been quietly delivering ratios to you since long before anyone had a name for the effect. Astronomers hit the identical wall a full century before Weber ever picked up a set of weights and solved it the same way without knowing they were solving the same problem. Ancient stargazers sorted the stars they could see into 6 rough classes of brightness, brightest to faintest, purely by eye, calling the very brightest first magnitude and the faintest visible without aid sixth. A system that survived, more or less unchanged, for roughly 2,000 years, when the Oxford astronomer Norman Pogson looked at how those ancient classes actually corresponded to measured light and formalized the relationship on purpose. He defined a difference of 5 magnitude classes as exactly a 100-fold difference in brightness, which makes each single step on the scale a multiplication by roughly 2.5. Not an addition. Pogson wasn't being elegant for its own sake. He was building, deliberately and mathematically, the same compression Weber had just described in a completely different field. because the raw range of starlight reaching Earth is far too wide for a linear scale to hold without becoming useless. Notice what all three of these, a hand holding a weight, an ear hearing a jet engine, an eye comparing two stars, have in common. None of them are failures of intelligence or training. They are properties of the equipment, consistent enough that entire measurement systems have been built around accommodating them rather than fighting them. The 2013 study mentioned earlier fits into exactly this lineage. 150 years later, on a completely abstract kind of magnitude that involves no weight, no sound, and no starlight at all. Just number words on a page. When Landy, Silbert, and Goldin asked adults to place 1 million on a line between 1,000 and 1 billion, the people who got it wrong were not failing at arithmetic. Every one of them could tell you, if you asked directly, that 1 million is 1,000 times 1,000. What failed was the felt sense underneath the correct fact. The same felt sense Weber found compressing weights and Pogson found compressing starlight, now compressing something with no physical substance at all, because the underlying machinery, it turns out, does not require the magnitude to be physical to compress it. It only requires the magnitude to be large. That is the specific, sourced, 3 times independently discovered mechanism sitting underneath tonight's title. A light year does not fail to register because it is a strange or foreign kind of quantity. It fails for the same structural reason $1 trillion and the brightest stars in the sky both fail, in a nervous system that has never once, in its evolutionary history, needed to represent something this large as anything other than a great deal. A quick word on what this is not, before moving on, because the shape of the claim matters. This is not a statement that some people are naturally bad at maths and others are naturally good at it. Landy, Silbert, and Goldin's participants who misplaced the numbers were not making arithmetic errors. Asked directly, most could correctly state that 1 billion is 1,000 million. What failed was not calculation. It was the felt sense underneath the calculation. And that gap between knowing a fact and feeling its size is precisely the gap this entire night has been mapping. It is worth pausing on why that evolutionary point matters, rather than treating it as a throwaway line. Nothing in the environment a human nervous system was shaped by ever required, distinguishing a group of 40,000 from a group of 40 million. Both would have registered correctly as more than I can use, more than I can count, more than matters for the decision in front of me. The machinery that handles magnitude was tuned for a world of small counts and modest distances. How many people in the other camp? How far to the next water source? How many days until the fruit ripens? 1 trillion of anything was never on the exam. The fact that the same machinery can be pressed into service at all, stretched via language and notation far past the range it was built for, is closer to a minor miracle than a design flaw. And the compression documented tonight is simply the seam where that stretching runs out of slack, which raises the obvious next question, and it is the fair one to ask. If the limit is this well documented, has anyone actually tried to build a workaround? A real one, not a slogan. And does it hold up under a fair test? The most natural fix, and the one nearly every science teacher reaches for first, is to stop stating the raw number and translate it into something the listener has already stood next to. That is not a bad instinct. When a comparison works, it is the single most efficient tool available for handing someone a size, and it deserves a completely fair trial before we decide whether it survives contact with a light year. Start with something genuinely long and genuinely real. The Trans-Siberian Railway, which runs from Moscow to the Russian Pacific coast, a single continuous line just over 9,200 kilometers in length. Roughly a week of continuous travel by train, the longest railway journey on Earth. Somewhere in a carriage on that route, right now, someone is watching birch forest slide past a window for the better part of a week, which is about as close as a human life gets to personally experiencing 9,000 kilometers from the inside. 1 hour of scenery at a time. Divide a light year by that distance, and the answer is just over 1 billion. 1 billion Trans-Siberian railways, laid end to end, laid across the width of a single year of light. Say it slowly, and it sounds almost manageable. Because 1 billion is a phrase you have said before. It is not manageable, and the previous chapter already told you why. 1 billion is exactly the kind of number that Landy, Silbert, and Golden found people misplacing on a line. The number that gets treated as merely one more big word, rather than a quantity 1,000 times larger than the million sitting just below it. The comparison did real work. It anchored one end of the sentence in something concrete, a railway you could look up, ride, photograph. But the other end of the sentence, the 1 billion doing the multiplying, landed exactly where the earlier demonstration predicted it would. Nowhere. Try a shorter anchor and see if the problem improves. The distance from the Earth to the Moon is about 384,000 kilometers, and it is one of the few great distances most people have some working relationship with, if only because a crewed mission has actually made the trip. A light year is about 24,600,000 of those. 24 million Earth-Moon distances, one after another. The anchor here is better. The Moon is vivid, specific, familiar, but the multiplier has simply moved from the billions into the tens of millions, which is still deep inside the region where the previous chapter's mechanism erases the difference between numbers that are, in reality, wildly apart. It's worth noticing where comparison still works cleanly before watching it fail, because the boundary itself is informative. Mars, at its closest, sits a little under 60 million kilometers from Earth, a distance space agencies openly discuss in months of transit time, and one that at least stays inside the range where twice as far and 10 times as far still means something to a listener. Neptune sits roughly 75 times farther than that, and the comparison still basically holds together. A listener can accept that reaching the edge of the planetary system is a wildly bigger undertaking than reaching Mars, and feel the difference in kind. Comparison is not broken in general. It is broken specifically past the point where the multiplier itself crosses into the compressed region documented a few minutes ago, and the distance to even the nearest star sits roughly 9,000 times farther than Neptune, which is exactly the point where the method stops translating and starts merely gesturing. Shrink the anchor again, down to the distance between the Earth and the Sunday. About 150 million kilometers, the distance light itself crosses in 8 minutes and 20 seconds. A light year turns out to be a little over 63,000 of those. 63,000 feels, for a moment, like the first genuinely graspable number of the night. It is roughly the seating capacity of a large stadium, a crowd size a person could stand in front of and believe. But look at what had to happen to get there. The anchor itself, the distance from the Earth to the Sun, is not a length anyone has any bodily relationship with either. Nobody has stood at one end of an astronomical unit. The comparison bought a smaller multiplier by spending an anchor that was never actually graspable in the first place. It just felt that way because the number attached to it was smaller. Try the chain on the actual nearest star system to the Sun, Proxima Centauri, whose distance has been pinned down by the European Space Agency's Gaia mission. A spacecraft this night will return to properly before the end, at 4¼ light years, or 268,000 astronomical units. 268,000 Earth-Sun distances, stacked end to end, just to reach the closest neighbor we have. The figure is precise, checkable, and utterly unfelt, for the same structural reason as every other multiplier so far. It sits deep inside the exact range where 1,000 and 1,000,000 and 1,000,000,000 have already been shown to blur. This is the actual failure mode, and it is worth naming precisely, because it is not that comparisons are dishonest or badly chosen. A comparison is a chain with exactly two links: an anchor the body has met, and a multiplier the mind can hold whole. At interstellar scale, you can always shorten one link, but only by lengthening the other, because the total distance being described never changes. Push the anchor down to something as small and familiar as a football pitch, roughly 100 meters, and the multiplier explodes to 9.5 trillion, the same trillion the money test broke 30 minutes ago. Push the anchor up to something whose multiplier finally looks reasonable, and the anchor itself stops being anything a person has ever stood inside. It helps to see the failure laid out as a simple table rather than a run of sentences, because the pattern becomes almost mechanical once it's visible. A railway, a familiar anchor, a billion-scale multiplier. The moon, a more familiar anchor, a multiplier in the tens of millions. The Earth-Sun distance, a barely familiar anchor, a multiplier in the tens of thousands. Every step right shrinks the multiplier by roughly 1,000 and simultaneously erodes the anchor's own familiarity by a comparable amount. The two columns trade against each other with almost eerie consistency, as if some fixed total were being conserved and merely reshuffled between them, which, in a real sense, is exactly what is happening. There is no length of chain that avoids this trade, because the trade is not a flaw in any particular comparison. It is a restatement, in a different grammar, of the exact compression documented in the previous chapter. Every comparison for an interstellar distance is secretly asking you to hold two things at once: a familiar anchor and an unfamiliar multiplier. And the multiplier, at this scale, is always recruited from the same crowded region of the mind where 1 billion and 1 trillion already refuse to tell each other apart. You can watch the consequence of this happen in real time in almost any documentary that reports one of these distances aloud. A narrator says a particular galaxy sits some enormous number of light years away, and the sentence lands as extremely, seriously far, which is correct, and also indistinguishable from the sentence that would have been produced by a number 1,000 times smaller or 1,000 times larger. Say that one galaxy sits 2 million light-years off, and a second sits 2 billion, and notice, honestly, what survives in memory 5 minutes later. Almost never the 1,000-fold gap between them. Usually just two separate impressions of far, filed in adjacent drawers that feel, on reflection, almost identical. The adjective survives the sentence. The multiplier, almost without exception, does not. A closely related mistake is worth naming too, because it appears constantly in casual conversation about space, confusing further with worse, or assuming that because two comparisons both fail to produce a feeling, they must be reporting roughly similar situations. They are not. A comparison that fails because the multiplier is in the millions, and a comparison that fails because the multiplier is in the trillions are reporting genuinely different physical situations, even though both failures feel identical from the inside. Keeping that distinction alive on paper, in the arithmetic, even when it cannot be kept alive as a felt sensation, is most of what separates careful science communication from merely impressive-sounding size talk. There is a particular kind of comparison worth flagging separately, because it is common and it fails in a slightly different way. The comparison that swaps one incomprehensible number for another, smaller-looking one, without actually reducing the underlying magnitude at all. Saying a light year is 63,000 times the Earth-Sun distance sounds, on the page, like progress. 63,000 is a smaller string of digits than 9 trillion. But no comprehension was gained in the swap. Only compression of the printed form. The astronomical unit itself was never graspable to begin with, so multiplying it by a smaller-looking number does not produce a graspable result. It produces a shorter sentence describing an equally ungraspable one. That distinction between a number that looks smaller and a quantity that is actually easier to feel turns out to matter for almost every method left to try tonight. So the honest verdict on this method is not that it is worthless. Nothing said tonight suggests anyone should stop using comparisons in ordinary life. They remain the single best tool available for teaching shape, category, and relative scale, and every science communicator who reaches for one is making a reasonable choice. A well-chosen comparison genuinely does teach shape. It can correctly tell you that the space between stars belongs to an entirely different category of size than the space between planets, and that is real, useful structure. What it cannot do, no matter how carefully the anchor is chosen, is deliver a felt magnitude, because felt magnitude is exactly the thing that was never available to borrow. It's tempting, at this point, to suspect the problem is simply insufficient creativity, that somewhere out there is the one perfect comparison nobody has thought of yet, the anchor clever enough to finally close the gap. That suspicion is worth taking seriously precisely because it feels so reasonable, and precisely because it is wrong for a reason that has nothing to do with creativity. Every possible anchor is drawn from the same finite stock of things a human body has actually experienced, and every one of them sits enormously closer to a doorway than to a light year. No comparison waiting to be discovered escapes that arithmetic, because the arithmetic is fixed by what a body has done, not by how cleverly a sentence is constructed around it. If comparison fails because it always needs a multiplier too large to feel, there is an obvious next move. Get rid of the multiplier altogether, by shrinking everything. The whole system, distance and objects together, down to a single, uniform scale, small enough to fit inside a room. Here is the method, and it is a genuinely different idea from the last one. Instead of comparing the distance to something familiar, shrink the entire solar system, every object in it, every gap between them, by the same fixed factor, so that the proportions survive perfectly and only the size changes. This is not a purely theoretical exercise. Scale models of the solar system have been built, physically, in parks and along riverside paths in cities around the world, precisely because a diagram on a page cannot do what walking a real distance does. A model built along a road can put the sun at one end as a sphere the size of a large exercise ball, Mars as a marble a short walk further on, and Neptune as a pea at the far end of a genuine afternoon's walk. And visitors who complete the walk consistently report that the emptiness between the planets registered in their legs in a way no textbook diagram had managed. The question is only how far it keeps working once the model is pushed from planetary to interstellar scale. Choose the factor by starting with the sun, because the sun is the one object in this story large enough to anchor a model properly. Shrink it down until it is the size of an ordinary 2-centimeter coin. Do that consistently, apply that exact ratio to everything else in the picture, and see what happens to the rest of the night's numbers. Earth, at that scale, becomes a speck about 220 micrometers across, roughly the size of a fine grain of beach sand, smaller than the point of the pin you'd need to mark its position. It orbits the coin at a distance of about 2.5 meters, which is to say the entire Earth-Sun system, at this scale, fits comfortably inside a living room with Earth as a grain of sand circling a coin on a coffee table. Push out to Neptune, the outermost planet, and its orbit becomes a circle a little over 75 meters across, the length of a decent sprint, the far end of a car park. That is the whole solar system. A coin, a scatter of motes too small to see without help, contained in a footprint you could stake out on a sports field. Now keep going, because the entire reason for building this model was never the solar system. It was the star. At this same fixed scale, the sun as a coin. A light year works out to a little over 160 kilometers. Proxima Centauri, the real nearest star system to the sun, sits 4.25 light years away, which puts it at this scale a little under 700 kilometers from the coin, roughly the driving distance between two cities in different countries. Stand next to your coin-sized sun with its grain of sand Earth 2.5 meters away, and the nearest other star's coin is most of a day's drive in any direction across terrain containing, at this scale, nothing else at all. Before leaving the coin behind, it's worth checking in on the smaller members of the Lighttime family mentioned at the very start of the night, because they behave themselves beautifully at this same scale, and the contrast is the whole point. A light second at the sun's coin-sized scale comes out to about 5 millimeters. A grain of rice. A light minute is about 31 centimeters. A ruler's length, a light hour stretches to roughly 18.5 meters, the length of a modest swimming pool. All three sit comfortably inside a room. Matching lengths you could genuinely lay a tape measure against. There is something almost funny about it. Once you notice, the family of units gets along fine right up until the final member joins it. And then the scale that worked perfectly for a rice grain, a ruler, and a swimming pool suddenly demands a 160-kilometer drive. That is real information. And the model earned it honestly. It says, correctly, that the gap between one star and its nearest neighbor is not merely bigger than the gap between a planet and its sun. It belongs to an entirely different category of emptiness, roughly 400,000 times larger by this particular ratio, and no comparison from the previous chapter delivered that shape nearly this cleanly. Stand in the room holding your coin, your grain of sand, Earth 2.5 meters away, and look toward the door. Whatever lies beyond that door, the hallway, the street, the rest of the city, none of it is where the next star is. The next star, at this scale, is past the edge of the neighborhood, past the edge of most journeys a person takes in an ordinary month. But notice what you can no longer see. The coin is fine. A coin is a normal object, and you can hold it. Everything else in the model has vanished below the resolution of an unaided eye, and no adjustment to the model fixes that, because the vanishing and the enormity are the same fact, described from two different ends. Test that directly by running the model the other way. Instead of anchoring the sun, anchor the distance. Set a light year to something walkable, say 500 meters, roughly the length of 6 or 7 football pitches laid end to end, a distance you could cover on foot in about 6 minutes. Apply the identical ratio backward and see what happens to the Sunday. It becomes about 75 micrometers across, the width of a single human hair held up to a bright window at the very edge of what a good unaided eye can resolve, and only just. Hold that hair up and squint, and you are looking at this scale, at the entire star that lights every clear sky you have ever stood under. Earth, at that same scale, becomes smaller than most bacteria. A mote you would need a microscope, not a magnifying glass, to find at all, and Neptune's orbit, the outer edge of everything the Voyager probes spent a decade crossing, shrinks to a circle you could trace with one finger on a placemat. Try a middle setting, just to be thorough, because it's tempting to assume some compromise point might split the difference. Make the sun the size of a basketball, about 24 centimeters across, big enough to hold, to bounce, to genuinely look at. At that scale, a light year stretches to about 1,600 kilometers, roughly the distance across a mid-sized country, and Proxima Centauri sits nearly 7,000 kilometers from your basketball, a long-haul flight away. The compromise does not produce a compromise result. It simply relocates the same trade-off to a size where neither half is comfortable. The sun is finally holdable, and the gap to the next star has become a transcontinental journey rather than a room or a highway. There is no setting of this dial that keeps both halves of the picture visible at once. Make the star walkable, and the sun disappears below, where light itself can usefully resolve it. Make the sun a real, holdable object, and the star becomes a day's journey away, across a landscape with nothing else in it. The model does not fail because it was built badly. It fails because the two things being modeled, the size of a star, and the space between stars are separated by a ratio so extreme that no single scale of measurement was ever going to display both ends at the same time. Run the numbers on any other pairing you like. A marble for the sun, a stadium for the sun, a mountain for the Sunday, and the same trade re-emerges every time, with only the specific units changing. That is not a limitation of the coin, or the room, or the person choosing the scale factor. It is the number itself, stated in the grammar of objects rather than the grammar of digits. And it says the identical thing the money did in the opening, and the railway line said 20 minutes ago. Some ratios are simply larger than the range your senses were built to hold in a single glance. It is worth being fair to the method one last time before leaving it behind, because it did something neither the money test nor the railway comparison managed. It produced a correct three-dimensional relationship all at once, rather than a single number read off a page. A person standing in the room with the coin and the grain of sand genuinely does come away knowing something true and structural about the solar system that a sentence of digits would not have delivered nearly as cleanly. The failure documented here is specific. Comprehension of the interstellar gap itself. Not a blanket failure of scale models as a teaching tool. There is one more repair worth trying, honestly, because it is the repair most people reach for once they've watched space fail twice. If the problem is specifically spatial, if it is about kilometres and meters and coins on a table, then perhaps the fix is to leave space behind entirely and ask the question in a currency the body already understands: time. You have waited for things. An hour has a felt weight that a meter does not, because you have sat through hours, and you have never once sat through a meter. So take tonight's distance and stop asking how far. Ask, instead, how long, using real, checkable speeds, not imaginary ones, so the comparison stays honest. Start with the most ordinary speed available. A car on a motorway holding a steady 120 kilometers an hour, the kind of driving that eats an afternoon and leaves a full tank noticeably emptier. Cover a light year at that pace, never stopping for fuel, sleep, or a single red light, and the trip takes about 9 million years. Longer than modern humans have existed as a species. Longer than the genus we belong to has existed, stretching back into an era before anything resembling a hand had ever gripped a steering wheel. Now move to sound, because it is the fastest thing that regularly moves through your own environment. At sea level, sound travels at about 343 meters a second, fast enough that thunder always seems to arrive suspiciously soon after lightning. Let a sound wave carry the distance of a light year. Never losing energy, never stopping. It would need roughly 874,000 years. Move up to something built by engineers. A long-haul airliner cruises at somewhere around 900 kilometers an hour. Slower, curiously, than sound itself travels at sea level, which is part of why a sonic boom is still considered an event. Flying continuously, refueling instantly, never landing. About 1,199,000 years. Notice already what just happened, because it is worth catching in the moment rather than after the fact. The airliner is meaningfully slower than the speed of sound. The ratio between them is real, and it matters enormously to anyone designing a wing. And yet the two durations you just heard, 874,000 years and 1,199,000 years, do not feel like they are reporting a real difference at all. They feel like the same sentence said twice. That is the identical compression from the very start of the night, now wearing the costume of a stopwatch instead of a bank balance. There's a particular irony worth noticing here. Because duration is supposed to be the one domain where your instincts are actually good. Ask a person to guess, without a clock, whether 90 seconds have passed, and most people land impressively close. Waiting rooms and traffic lights have trained that skill into nearly everyone. Ask the same person to compare two long past durations. say, whether a given ancient site is closer in time to another ancient site or to the present day. And the accuracy collapses completely in a specific, well-documented direction. Everything further back than living memory gets pulled toward a single, undifferentiated long ago. The way a bright torch and a floodlight both eventually just read as very bright once they're far enough, past what your eye's aperture can usefully distinguish. Your sense of duration is excellent at the scale of a red light and useless at the scale of a millennium, and a light year, converted into years, sits so far past a millennium that the two failures are barely worth distinguishing. Leave the atmosphere. The International Space Station orbits Earth at roughly 7 2/3 kilometers a second, about 27,000 kilometers an hour, fast enough to circle the entire planet in 90 minutes, fast enough that its crew watches a sunrise roughly every hour and a half, 16 of them in a single working day up there. At that speed, a light year takes about 39,100 years, long enough that a crew member launched at the start of the trip would, by the time it ended, have missed the entire span of recorded human writing, arriving instead somewhere in the last cold centuries of the most recent ice age. And now, the fastest real object human engineering has ever produced. Parker Solar Probe launched in 2018, carrying a heat shield built to face temperatures near 1400 degrees Celsius, while keeping its instruments tucked just behind that shield, running at close to room temperature. An engineering problem closer to holding a blowtorch an arm's length from your face than to anything in ordinary spaceflight. It reaches its extreme speeds by repeatedly using Venus's gravity to tighten its orbit, diving a little closer to the Sun on each pass. On the 24th of December 2024, it made its closest approach yet, passing about 6 million kilometers above the Sun's surface and reaching a recorded speed of 192.22 kilometers a second, nearly 700,000 kilometers an hour, the fastest anything built by human hands has ever traveled. That speed is not something the spacecraft can sustain. It exists only for a matter of hours at the bottom of the Sun's gravity well and cannot be carried anywhere else in the solar system. But grant it honestly, as a ceiling, at that pace, held indefinitely, a light year would take roughly 1,560 years. There is a specific pleasure in that last figure worth pausing on before moving forward. Separate from what it says about a light year, a spacecraft skimming an active star at nearly 700,000 kilometers an hour, surviving heat that would vaporize most engineered materials, using nothing but a carefully angled shield and careful timing. That is a genuine, hard-won achievement of the kind this channel exists to notice, entirely apart from whatever it does or does not teach us about comprehension. It is worth admiring on its own terms for a moment before returning to the harder question. Sit with those 5 figures side by side for a moment, because the shape they make together is the actual finding. A car, 9 million years. Sound, 874,000. A jet, 1,199,000. The space station, 39,100. The fastest machine ever built, 1,560. The ratio between the slowest and the fastest of those 5 is well over 5,000 to 1. A gap on the order of the one between a single step and a flight halfway around the planet. And yet, heard in a sentence, all 5 durations occupy the identical emotional register. Unfathomably, hopelessly long. None of them feels 5,000 times longer than any of the others. They feel like 5 ways of saying the same word. Run the arithmetic one further step, and the point sharpens rather than softens. The ratio between the space station's speed and Parker Solar Probe's record speed is about 25 to 1. The space station orbits at a meaningful fraction of the probe's extraordinary velocity. Not a trivial one, and yet 39,100 years and 1,560 years produce almost the same wince when spoken aloud. The same slow exhale, the same mental shrug toward an inconceivably long time. A 25-fold gap collapsed into indistinguishability by the identical machinery that already flattened a 1,000-fold gap between $1 million and $1 billion. That is not a coincidence, and by now, you have the vocabulary to name exactly what it is. Converting the distance into time did not remove the compression documented 3 chapters ago. It relocated it from kilometers into years, using the identical machinery, because the machinery was never about kilometers in the first place. It compresses whatever magnitude it is handed, and a duration is just another magnitude wearing a different unit. Before moving past these 4 figures entirely, it's worth naming one honest complication in how they were built, because tonight has been careful about honesty everywhere else. None of these speeds could actually be sustained the whole way. A jet needs fuel, a body needs food, no engine runs forever without maintenance. Every one of these numbers is a clean hypothetical. Hold this speed, without interruption, for as long as it takes. That is a fair and standard way to compare rates, the same convention used throughout this episode's other calculations. But it is worth being explicit that these are best case, uninterrupted figures, not journeys anyone could actually complete. There is, however, one genuine difference between what just happened and everything that came before it, and it is worth taking seriously rather than dismissing. Durations, unlike kilometers, are made of something you have actually lived through. A year has weather in it, and a season, and a birthday. 874,000 years does not feel large the way 1 trillion kilometers felt large. It feels, for a strange moment, almost inhabited, because year is a word your own life has content for, even when the number in front of it does not. That feeling is real, and it is worth chasing carefully, because it points at something the earlier methods never touched. Not a bigger number, but a smaller and much more interesting one. The single largest duration a human being has ever actually held. Somewhere under everything measured tonight, your pulse has kept counting, the way it has since before you owned a watch or knew what a watch was for. At rest, it lands somewhere around 60 to 100 beats a minute for most adults, a narrow enough range that it has served, across every culture that ever needed to time something without a clock, as the one rhythm nobody has to be taught to notice. It is the smallest unit of time you own, in the most literal sense possible. A clock built into you, requiring no instrument, that you can consult right now by pressing 2 fingers to your wrist and simply waiting. It is worth noticing that the same impulse that keeps you counting a pulse without being asked is the impulse that built the pendulum clock Roma used in that unheated Paris observatory almost 350 years ago. A mechanical heartbeat, swinging at a fixed, countable rate, standing in for a human one that tires and drifts. Roma needed a rhythm precise enough to catch minutes of difference in a shadow arriving late. You have been carrying a cruder, older version of the same instrument in your chest the entire time. A year is the pulse's opposite number, and it is worth asking, seriously, why a year, and not a decade, not a century? Turns out to be the largest duration that works the same way. You have lived several dozen of them, and crucially, you have lived more than one, which means you can genuinely compare, in a way that does not require calculation. That last year did not feel like the one before it. A year has a shape you can walk through in memory. A stretch where evenings arrive early, a stretch where they refuse to end, a month tied to a particular slant of light on a particular wall. Ask yourself for the middle of last year, and something specific comes back. Not a date, necessarily, but a texture, a season, a mood the air had. Push the same request one notch further, and the shape collapses. Ask for the middle of the last decade, and almost nothing arrives on demand. Perhaps one sharp memory standing in for thousands of unremembered days, which is already the sign that the decade has stopped being a lived thing and started being a label, the same way 1 billion is a label rather than a felt count. A year is the last rung on a ladder that goes all the way down into the body. A decade is already one rung above where direct experience runs out. That makes the year a strange and specific kind of unit, not simply a long time, but the literal ceiling of felt duration, the largest quantity of anything that a human being routinely holds, examines, and compares against another instance of itself. Above a year, everything is built out of years the way everything above 1 trillion is built out of the same 3 or 4 number words, assembled by language rather than delivered by direct experience. Which means whoever built tonight's unit out of light in a year did not pick that ingredient carelessly. They reached, whether they said so or not, for the single largest thing available that a person could actually be assumed to already own. The top of the ladder, paired with the fastest rate that exists, multiplied together into a single word. It is worth naming, plainly, what that pairing cannot do. It cannot make the product of the 2 ingredients comprehensible, any more than multiplying 2 numbers you understand individually guarantees you will understand their product. A year contains a little over 31.5 million seconds, and knowing that fact does not hand you any felt sense of 31.5 million of anything. You understand a second, and you understand a year as a lived shape, but the number connecting them sits in exactly the compressed region documented at the very start of the night. A light year is not more graspable simply because both of its raw components, a rate, a year, happen individually to be things you can name. Comprehensible parts do not guarantee a comprehensible product any more than a comprehensible weight and a comprehensible distance guarantee a comprehensible amount of work done lifting it. But something did change, and it is worth being precise about what. The unit stopped being built entirely from the unfamiliar. Half of it, the year, is drawn directly from the one large duration your own life actually contains. That is not nothing, even though it is nowhere near comprehension. It is the first ingredient tonight that came from inside the body rather than from a laboratory, a satellite, or a printed table of digits. And it is going to matter enormously in a moment once we finally ask who assembled it and why they chose exactly this pairing, rather than any other one available to them. First, though, a harder and more honest question has to be answered, because it has been sitting underneath the entire night without being addressed directly. If no human being can hold a light year, not with money, not with railways, not with a coin standing in for the sun, not even with a year standing in for a duration, then how has any of astronomy's actual working measurement of these distances ever gotten off the ground at all? For roughly 200 years after Copernicus put the sun at the center of the solar system, the strongest argument against him was a measurement nobody could make. If the Earth genuinely orbits the sun, then the planet occupies 2 different positions, 6 months apart, separated by the full width of that orbit. A nearby star, viewed from those 2 positions, ought to appear to shift very slightly against the far more distant stars behind it. The same effect you get holding a finger at arm's length and closing one eye, then the other, and watching the finger jump against the wall behind it. Measure the size of that jump, and simple trigonometry hands back the star's distance, with no theory required beyond the geometry of a very long, very thin triangle. Astronomers searched for that jump for 2 centuries and found nothing, and the absence was used, reasonably, as evidence against a moving Earth. What almost nobody entertained seriously was the other explanation, that the jump existed and was simply too small for any instrument yet built to catch, which would only be true if the stars were separated from Earth by a distance so extreme it strained belief. It was true. Bessel was not the only astronomer chasing that angle in the 1830s. A handful of other observers across Europe were pursuing comparable measurements on other candidate stars in roughly the same years, using their own best instruments and their own best guesses about which stars might be close enough to show a detectable shift. That crowded field matters for the texture of the story, even though it does not change its outcome. The angle being hunted was so fine, and so easily buried under atmospheric shimmer and instrumental flex, that success depended as much on the specific quality of a given telescope and a given observer's discipline as on any theoretical insight. Being right about where to look was necessary. It was not sufficient. The angle finally caught up with an instrument in Königsberg in the winter of 1837 into 1838, in the hands of a German astronomer named Friedrich Wilhelm Bessel. He chose his target deliberately, a dim star called 61 Cygni, notable mainly because it crept across the sky faster than almost any other star on record, and fast apparent motion, Bessel reasoned, was the signature of proximity. He used a heliometer, a telescope whose lens is split cleanly down the middle so the two halves can slide against each other on a calibrated screw, letting an observer bring one star in one half image into exact alignment with a different star in the other, and read the angle between them directly off the screw. It is worth being honest about why the search had failed for 200 years before Bessel. Because the reasons are not a story about laziness or poor eyesight. The angle being hunted was smaller than anything the atmosphere itself would comfortably permit. Air is never perfectly still. It sits in restless cells of slightly different temperature and density, each one bending starlight by a slightly different amount, which is the entire reason stars twinkle and planets, being close enough to show a tiny disk rather than a point, mostly do not. That shimmer smears a star's apparent position by an amount that, across most of the 18th and early 19th centuries, was comparable to or larger than the very shift astronomers were trying to detect. Telescope tubes flexed slightly under their own weight as they tracked a star across the sky, by amounts that could swallow the signal whole. Every heroic attempt before Bessel was, in effect, trying to hear a whisper in a room full of static, using an instrument that added its own static on top. Bessel's heliometer was built to fight exactly that problem. Its objective lens was sawn cleanly in half along a diameter, and the two halves were mounted so they could slide against each other on a finely calibrated screw. Looking through it produced two overlapping images of the same patch of sky. Sliding the halves apart brought one star in one image into exact coincidence with a second, different star in the other, and the reading on the screw at that moment of alignment gave the angle between them directly, without needing to trust the absolute pointing of the whole instrument the way a fixed-lens telescope would. It had been built years earlier by Joseph von Fraunhofer, the finest optician in Europe at the time, and it turned a measurement that depended on holding an entire telescope rock steady into one that depended only on a much smaller, much more controllable motion. A screw, a hand, a practiced eye. Night after night through the winter of 1837 into 1838, Bessel took his readings in an unheated observatory, comparing 61 Cygni against two much fainter, apparently more distant companions nearby in the sky, chosen precisely because their extreme faintness suggested they sat far enough behind 61 Cygni to serve as a fixed, unmoving backdrop. Each night's work meant repeated readings of the same tiny angle, each one a small, exhausting act of judgment about whether 2 points of light truly coincided, followed by hours of arithmetic by candlelight to correct for atmospheric refraction, the flex of the tube, the temperature of the metal screw itself, which expands and contracts enough to matter at this level of precision. By the end of 1838, the pattern held steady across enough nights to trust, a shift of roughly a third of 1 second of arc, an angle equivalent to the width of a coin viewed from about 4 kilometres away, which corresponds to a distance of a little over 10 light years. It was the first distance to another star ever measured by a human being. The modern, more precise figure for 61 Cygni is closer to 11.5 light years. Bessel's instrument, working at the very edge of what a 19th century telescope could resolve, was still remarkably close. There is a small, human detail in the choice of comparison stars worth dwelling on for a moment, because it shows the same discipline that made the whole result trustworthy. Bessel did not simply measure 61 Cygni's position on the sky in isolation. Position alone, against no fixed reference, would have been useless, since the telescope, the building, even the Earth itself, was never perfectly still. He needed a backdrop assumed to be motionless, and he found it in two much fainter stars sitting nearby in the same field of view, reasoning that anything that dim was probably sitting so much farther away that its own parallax shift would be too small to matter, leaving it to serve as a fixed grid against which 61 Cygni's much larger shift could be read. That reasoning turned out to be correct, and it is a small, elegant example of exactly the kind of human-sized judgment this whole chapter is trying to illustrate. Not a leap of faith, but a specific, defensible inference, checkable by anyone who cared to repeat it. Notice exactly what Bessel did, and exactly what he did not do. He did not comprehend 11 light years. Nobody could have, for all the reasons already documented tonight, and there is no record of Bessel or anyone reviewing his work claiming otherwise. What he did was reduce an incomprehensible quantity to a sequence of entirely human-sized operations. Measure one small angle, using an instrument built for exactly that purpose. Measure it again 6 months later, from the other side of a baseline already known from other means, and apply a triangle, the same kind of triangle a surveyor uses to measure the width of a river without crossing it. Every individual step in that chain was something a trained person could genuinely hold in their mind, completely, with full understanding of its size, its precision, and its likely error. The distance that came out the far end was not required to pass through anyone's comprehension on its way to being correct. The triangle does not care whether the person solving it can picture the hypotenuse. It only cares whether the two known angles and the one known side were measured honestly. That measurement earned its own unit, eventually. A star whose position shifts by exactly 1 second of arc across that 6-month baseline is defined as 1 parsec away, about 3¼ light years, and the parsec has been the working currency of professional astronomy ever since, precisely because it is built from the measurement procedure itself, rather than from anything a listener needs to feel. In 2015, the International Astronomical Union fixed its value exactly at 648,000 divided by pi astronomical units, closing off the last trace of measurement, uncertainty in the definition, the way the meter itself had been closed off in 1983. That definition rests, in turn, on the astronomical unit itself, the Earth-Sun distance, which the same body had already fixed exactly. In 2012, building on decades of radar ranging that bounced signals directly off the surface of Venus and timed the echo, replacing an older chain of geometric inference with a number anyone could, in principle, rederive with a transmitter and a very good clock. Professional astronomers reach for the parsec, not the light year, for almost everything they publish, for the same reason a carpenter reaches for a tape measure rather than a story about how far someone once walked. Bessel's method did not stay a heroic, 1 star at a time undertaking for long. It became routine, then mechanical, then, within another century and a half, something an entire spacecraft could do without a single human eye ever looking through an eyepiece again. The European Space Agency launched a spacecraft called Gaia on the 19th of December 2013, sending it not toward any planet but toward a quiet gravitational balance point about 1.5 million kilometers from Earth, on the side facing away from the Sunday. Its entire purpose was Bessel's triangle, run automatically, at a scale no committee in 1838 could have imagined proposing. Gaia carried 2 telescopes fixed at a set angle apart, feeding a single detector built from very nearly 1 billion pixels. At the time, the largest digital camera ever sent into space, cooled and shielded well enough to hold its calibration steady across more than a decade of continuous operation, with no astronaut ever visiting to service it, the way the Hubble Space Telescope's instruments periodically were. It rotated slowly, once every 6 hours, with its spin axis itself drifting in a controlled pattern, so that over years of operation, every patch of sky eventually crossed its field of view from dozens of different angles. No star was measured once. Each was measured over and over, and every repeat measurement tightened the result a little further. The precision it reached is difficult to state without it sounding like exaggeration, so state it as an angle instead. Gaia's best position measurements are accurate to a few dozen millionths of a second of arc, an angle so small that resolving it is comparable to measuring the width of a single human hair from 1,000 kilometers away. Bessel spent a winter chasing a third of a second of arc with a screw-adjusted lens. Gaia was routinely catching angles 10,000 times finer than that, in the ordinary course of its mission, without anyone standing at an eyepiece at all. The mission ended its science observations on the 15th of January 2025. After more than 11 years in continuous operation, nearly twice its originally planned lifetime, extended repeatedly, because the spacecraft simply kept working and the data kept improving the longer it ran. And its most recent full data release contains position, distance, and motion information for roughly 1.8 billion individual objects. Notice too that the word doing the heavy lifting in the last 2 paragraphs was billion. The exact word the money test at the very start of the night showed you compressing without permission. Read past it just now, probably the way you read past $1 billion earlier, correctly, fluently, and without feeling the size of it at all. That is not a failure specific to this sentence. It is the same mechanism, caught again, in the middle of a story about the very instrument built to defeat it. Before Gaia, astronomers had trustworthy distances to a few 100,000 stars, painstakingly assembled across a century and a half of Bessel's method, performed by hand, and, later, by ground-based cameras fighting through a shimmering, unstable atmosphere. After Gaia, that number sits above 1 billion, gathered from a vantage point where there is no atmosphere left to fight. There is something worth sitting with in the shape of that operation, separate from the raw numbers. Bessel's measurement was, in every sense, a human event, a specific person in a specific cold room making a specific decision each night about whether 2 points of light truly lined up, aware the whole time of what was riding on the outcome. Gaia's measurements were not witnessed by anyone as they happened. For more than 11 years, the machine turned slowly in the dark, 1.5 million kilometers from Earth, running the identical geometric operation Bessel had performed by hand, over and over, unattended, indifferent to whether the result mattered to anybody. Nobody watched the moment any individual star's distance was pinned down. The catalogue simply accumulated, one silent repetition at a time, until it contained more verified stellar distances than the whole of human astronomy had produced in the preceding 2 centuries combined. The catalogue is not only a list of distances either, and it's worth naming what else came along for free. Because Gaia tracked not just where each star sat but how it was moving, the resulting data set turned out to contain the motion of our galaxy's disk, the shredded remains of smaller galaxies our own has slowly consumed over billions of years, and streams of stars still drifting together long after the star cluster that once held them gravitationally has come apart. A mission built to answer Bessel's one question, at scale, ended up handing astronomers a history of the galaxy's entire violent, ongoing assembly as a byproduct of measuring where things simply are. There is a specific, almost tender detail in how the mission ended that is worth including here, because it says something about the culture that builds these instruments. Rather than simply letting Gaia drift, abandoned, in an orbit that might eventually cross paths with a future mission, Its controllers deliberately maneuvered it into a stable graveyard orbit, venting its remaining fuel and disabling its transmitters in a carefully sequenced final set of commands. A controlled retirement for a spacecraft that had, by any measure, outperformed every expectation placed on it at launch. Consider what that actually represents against where this chapter began. The distance to a single star was the hardest unanswered question in astronomy for 2,000 years, unsolved by Aristotle, unsolved by Ptolemy, unsolved by 2 centuries of instrument makers working immediately after Copernicus. Bessel gave the better part of a year to one star and came home with one number, a single spacecraft. Spinning quietly at a point in space nobody visits, produced more than 1 billion numbers of the same kind, and most of the people whose job is to use that catalogue will never personally verify more than a handful of the individual entries in it. The distances are not a triumph to be marvelled at from a distance anymore. They are a look-up. Now ask the question this whole night has actually been circling, and ask it of the most precise instrument that has ever measured a star's position. Open the Gaia archive. It's public, and anyone can query it, and pull the entry for a nearby star. You'll get a distance in light years or parsecs with an uncertainty attached so small it barely matters for any ordinary purpose. Ask the person who built that instrument, or the person who wrote the software that reduced its raw data into that final number, whether they can picture the distance itself, hold it, feel its size, the way they might feel the length of a hallway. They cannot. Astrometrists who work with this catalogue for a living will tell you so plainly, without embarrassment, and then talk at length and with real enthusiasm about something else entirely. The error budget, the systematic corrections, the specific stars in the catalogue whose reported distances they personally would not trust without a second check. That is where their understanding actually lives, not in the magnitude the instrument reports, but in the procedure that produced it, which is human-sized from beginning to end, and which they know completely. The story is not even finished. Gaia's own team is still working through more than a decade of accumulated observations. A further data release, built on tens of months more data than the current public catalogue, is expected in the coming months, and a final release drawing on the mission's entire 11-year run is still years away from completion. The spacecraft itself has already been retired, moved into a quiet graveyard orbit where it can do no more harm to future missions passing through the same region of space. Its instruments switched off for good, but the numbers it gathered will keep being mined, refined, and republished for a working lifetime yet by astronomers who were graduate students when it launched and will be senior scientists by the time its last data release is finally exhausted. Gaia did not fail to deliver comprehension. It was never asked to. It was asked to measure, and it measured better than any instrument in history. A total, unambiguous victory for one specific operation run 1 billion times over that leaves the operation this whole night has actually been testing exactly as far out of reach as it was when Bessel first picked up his heliometer. 6 real methods, spanning 3.5 centuries, a live demonstration with money, a comparison to a railway, a coin standing in for the sun, 4 honest conversions into travel time, 1 dedicated astronomer's winter, and 1 spacecraft's decade of silent, precise rotation. Every one of them produced a correct, checkable, defensible result. Not one of them produced a felt sense of the actual size, laid side by side, that stops looking like 6 separate disappointments and starts looking like something else entirely. Lay the 6 attempts next to each other and look for what changed between them, because something was altered every single time, and one thing never was. The money test changed the unit to something emotionally loaded. The railway comparison changed the anchor to something walkable and familiar. The coin model changed the scale of the entire physical world at once. The travel time conversion changed the dimension itself, from space to duration. Bessel changed the method, replacing imagination with a measured angle. Gaia changed the operator, replacing a person with an instrument capable of repeating that operation 1 billion times without fatigue. Every variable available was altered by somebody, at some point, honestly and skillfully. Except one. Nobody, across 3.5 centuries of trying, ever touched the actual definition of the word understand. All 6 attempts quietly assumed that understanding a size means the same thing at a light year that it means at 3 meters. That assumption is the actual fault line, and it has been sitting underneath the entire episode, undetected, because it never announces itself. It simply produces the same specific flavor of failure, no matter which method goes looking. This reframes every single chapter of the night, retroactively, as one long, controlled experiment, rather than 6 separate anecdotes. The money test removed the astronomical setting entirely, and the failure persisted. The railway and the astronomical unit comparisons changed the anchor, and the failure persisted. The coin model changed the entire sensory channel, from language to a 3-dimensional object you could theoretically touch, and the failure persisted. Travel time changed the dimension from space to duration, and the failure persisted. Bessel and Gaia changed the operator from an unaided mind to an instrument of extraordinary precision, and the failure of comprehension, specifically, not of measurement, persisted through that too. A variable that keeps producing the same outcome no matter how thoroughly it is altered is not a variable causing the outcome. It is a fixed feature of the system the experiment was run inside. Look at what understanding a size actually consists of. In any case where it succeeds, understand the height of a doorway, and you are not running a calculation. Your body already knows, without being asked, whether ducking is required. Understand the weight of a full kettle, and your arm has already anticipated what lifting it will cost before your hand closes around the handle. In every case that works, understanding turns out to be a successful match between the new quantity and something already stored, usually something the body itself has carried, lifted, walked, or weighted through. The match does not need to be exact to succeed. It only needs to be close enough that the stored experience can stand in for the new one without the mind noticing the substitution. Which is precisely why the failures documented tonight are not failures of precision. They are failures to find any candidate for the substitution at all, at any distance from exactness. That is also why a genuinely large quantity can sometimes still be understood, as long as the match exists. A marathon is 42 kilometers, and almost nobody can picture 42 kilometers laid out as a line. Nearly everyone can understand a marathon anyway, because they have walked for an hour, felt what that hour cost their legs, and can multiply that felt cost by most of a day. The stored quantity being matched was never the distance. It was the fatigue. The same test works in the other direction, on a quantity most people assume they understand, and mostly do not. Ask someone to picture the population of the world, a little over 8 billion people, and what usually arrives is not 8 billion of anything. It's a vague impression borrowed from the largest crowd that person has personally stood inside. A packed stadium, a busy station platform, a festival crowd, stretching further than the eye can resolve individual faces. That borrowed image is doing real work, and it is also wrong by a factor of roughly 100,000, because a large stadium holds perhaps 80,000 people, and the gap between 80,000 and 8 billion is exactly the kind of gap the crowded mental ruler cannot represent. The image feels like understanding. It is actually a stand-in, borrowed from the nearest available memory, stretched far past where it remains accurate. And once you know to look for that substitution, you start noticing it everywhere large numbers get discussed, as though they had been genuinely pictured. Now run that same search against 9,460 billion kilometers, or against any of its 6 disguises from tonight. $1 trillion, 1 billion railway lengths, a coin's width sun with its neighbor 2 countries away, 1 million years of continuous flight, an astronomer's one measured angle multiplied 1 billion times over. There is no stored bodily experience anywhere in a human archive that stands in a usable relationship to any of them. The search does not come back slow, it comes back empty. And it comes back empty every time, regardless of which costume the number is wearing when it arrives. Because the failure was never really about kilometers, or dollars, or years. It is about the operation of matching itself, which requires a partner quantity that this magnitude has never had and structurally cannot have. Precision matters about exactly who this applies to, rather than overselling the claim into something tidier than the evidence supports. In that 2013 study, a little under half of the adults tested did place the large numbers correctly, spaced out in genuine proportion to their size. Trained habits, mathematical practice, and sheer familiarity with scientific notation clearly help, and some people do build a more accurate felt sense of enormous magnitudes than others manage. But helped is not the same claim as solved. Even the participants who placed the numbers correctly on a printed line were not reporting a felt sensation of 9 trillion the way they'd report the felt sensation of a flight of stairs. They were applying a learned rule correctly, which is a genuine skill, and a different operation entirely from the bodily match this whole night has been chasing. Practice moves the boundary. Nothing found so far in any study cited tonight moves the underlying mechanism. It also explains something that might otherwise seem strange. Why the failure felt so consistent across 6 wildly different attempts, using 6 wildly different tools, built by people, separated by centuries, and with no knowledge of each other's work. A shared cause produces a shared signature. The signature here, a correct number, confidently produced, sitting completely outside any felt sense of its own size, showed up in a live demonstration with money, in a railway line, in a coin standing in for the sun, in 4 honest speeds, in one astronomer's patient winter, and in one spacecraft's silent decade. Because in every one of those 6 cases, the same missing ingredient was missing. That is the honest answer to tonight's title, complete and fully supported now, rather than merely asserted. Yes, it is so vast you cannot comprehend it, and the reason is not effort, and it is not a better analogy waiting to be discovered by someone cleverer than the 6 approaches tested tonight. It is a structural absence, a distance so far outside the range of anything a body has ever held that no method, however carefully built, could ever manufacture the missing partner from scratch. It is worth being precise about what has and has not been claimed here, one final time, before moving forward. Nothing in tonight's argument says the universe is somehow unknowable, or that science has hit a wall it cannot cross. Every single distance discussed tonight is known, to remarkable precision, by people who worked hard and honestly to establish it. The wall is entirely on the receiving end, in the specific, narrow operation of turning a known, correct number into a felt sensation, and nowhere else. Measurement kept working perfectly this whole time. Only comprehension stalled, which leaves exactly one honest question still open. And it is a bigger one than the title originally asked. If no one, not Bessel, not the engineers who built Gaia, not you, right now has ever comprehended these distances, why does the unit exist at all? Why build a word specifically shaped like something you already lived through and hand it to millions of people who would use it fluently for a century and a half if the thing it names could never actually be felt? That question deserves to be sat with for a moment rather than rushed past, because it is genuinely strange once noticed. Plenty of technical fields carry jargon nobody outside the field understands, and that jargon simply stays inside the field, unused by anyone else. The light year did the opposite. It escaped the observatory almost immediately, and within a lifetime it was appearing in newspapers, school books, and casual conversation, spoken confidently by people who had never once needed to solve a triangle. Something about the specific shape of the word made it want to spread. in a way most technical units never do. And that is exactly the kind of clue that points toward a deliberate act of design rather than an accident of terminology. The answer is not philosophical. It is historical. It is documented. And the person responsible left a written record explaining exactly what he thought he was doing. The word was not built at a telescope. It was built at a writing desk. For readers who were never going to own one, his name was Otto Uhle, a German science writer, not an astronomer by training, who made his career translating the discoveries of others into language ordinary readers could follow, and who would go on, the following year, to co-found Die Natur, which became the leading popular science magazine in the German-speaking world. In 1851, he published an article titled Was wir in den Sternen lesen, aimed squarely at people who had never looked through a telescope and had no intention of starting. He was writing into a specific moment. The 1850s were the decade popular science became a genuine mass product in the German-speaking world for the first time. Cheap printing, a growing literate middle class hungry for the discoveries filling scientific journals nobody outside a university could otherwise read, and a small cohort of writers, Uhle among the most prominent of them, whose entire profession was translation in the broadest sense, taking a result that had cost someone else a career to obtain and finding the sentence that would let a shopkeeper or a schoolteacher carry it home intact. His problem, in that context, was not accuracy. Every figure he needed already existed, expressed correctly in the units astronomers of the day actually used. Distances in German miles, strings of digits long enough to require a second breath just to read aloud. His problem was delivery. He had one pass, in prose, with no diagram and no follow-up lecture, to get a genuinely enormous quantity into a reader's head in a form that reader could then repeat to someone else without dropping it. The stellar distances Uhle had available to write about were themselves barely more than a decade old. Bessel's measurement had appeared in 1838. Uhle was writing in 1851. He was, in a real sense, one of the very first popularizers ever tasked with explaining a stellar distance to a general readership at all. There was no existing tradition of plain language astronomical writing about interstellar space for him to borrow from, no established idiom. Because the numbers themselves had barely finished being measured, he was building the vocabulary and using it in the same article. So he reached for a word, Lichtjahr, a light year. He knew it looked strange on the page, a unit of distance whose name ends in a word for duration. And he addressed the strangeness directly, rather than hoping nobody noticed. He pointed his readers toward a phrase they already used without any confusion at all. The Wegstunde, literally a walking hour. An ordinary distance expressed as the length of ground a person covers on foot in an hour. Nobody found that construction odd. Everyone already understood that an hour's walk is a length, not a duration, once it is used that way. Uhle was doing precisely the same trick, with a faster traveller and a longer clock. Light instead of a walker. And a year instead of an hour. The English form of the word followed in 1864, appearing in the monthly notices of the Royal Astronomical Society, 13 years after Uhle's German original, and from there it moved into every language that talks seriously about the sky. Spanish, French, Russian, Japanese, each adopting some local equivalent of the same two-part construction, a substance and a duration welded together into a single unit that no working physicist would have designed from scratch. Now, set that origin next to the entire rest of tonight, because it changes what the unit actually is. Uhle was never trying to make the distance comprehensible. There is no indication anywhere in his writing that he believed that was achievable, and by every method tested across the last hour and a half, it is not. What he was after was narrower and, in its own way, more useful. He wanted the quantity to be sayable, repeatable, teachable, transportable, from one head to another, without collapsing into a string of digits nobody could hold on to for more than a sentence. Professional astronomy noticed the difference almost immediately and largely declined the trade. The parsec Bessel's unit, built directly out of the measurement procedure itself, remained the working currency of the profession because it converts cleanly between what an instrument observes and what a paper reports, with no extra constant floating in the middle. Arthur Eddington, one of the most influential astrophysicists of the early 20th century, was openly dismissive of the light year on exactly these grounds, considering it clumsy for serious work and fit mainly for the popular page. It is a small irony that Eddington's own most famous public moment, leading the 1919 expedition that confirmed Einstein's prediction about light bending around the sun during a total eclipse, depended entirely on the kind of vivid, plain language storytelling that made general relativity a household topic almost overnight. He was, in his own way, also in the business of translation for a wide audience. His objection to the light year was not a rejection of popular science. It was a much narrower complaint about which specific unit belonged in a technical paper. And it is worth taking seriously rather than waving away. A unit built from a duration is awkward to combine with the other quantities a working physicist actually needs: velocities, masses, gravitational calculations. All of which are far cleaner in a unit derived straightforwardly from length. From inside the discipline, Ulle's handle looked like an amateur's shortcut dressed up as a measurement. He was not wrong on those terms. And the word survived his objection anyway, for a reason that has nothing to do with what astronomers need. The light year was never built as a scientific instrument. It is a communication device, built on purpose out of the only two materials available that a person could be assumed to already possess: a substance everyone has watched arrive, and the one duration a human life has ever actually held in full, examined from the inside and compared against another instance of itself. The title of tonight, understood properly now, was never a complaint about a limitation in you. It is an accurate description of the conditions under which the unit was manufactured. A light year exists because the distance it names cannot be comprehended. The word is not a failed attempt at making it graspable. It is the workaround, a handle bolted onto a weight nobody was ever going to lift, built by a man who understood exactly what he could give his readers and exactly what he could not, and who gave them the first one anyway. There is one operation left tonight that nobody has tried yet, and it is the only one that actually works. Not because it is cleverer than the other 6, but because it does not ask you to hold anything at all. Every method so far has asked something of your mind. Picture this. Compare that. Calculate the other thing. This last one asks nothing. It has already happened, is happening now, and will keep happening whether you attend to it or not. Go outside, if the sky where you are happens to be clear, and look toward the northern part of the sky, high overhead in the months around summer in the northern hemisphere, lower toward the horizon in winter. Look for a bright white-blue point, one of the brightest stars visible from anywhere on Earth, sitting at one corner of a large, easy triangle formed with 2 other bright stars, a pattern skywatchers call the Summer Triangle, and Vega is its brightest and most northern corner, the anchor star of the small, otherwise unremarkable constellation Lyra. That is Vega, the 5th brightest star in the night sky, and one of the very first stars, back in Bessel's era, whose distance was pinned down at all using exactly the parallax method described an hour ago. It has served, for most of the history of modern astronomy, as a kind of reference point for brightness itself, the star against which the entire magnitude scale from earlier tonight was, for generations, effectively calibrated, the zero from which every other star's brightness was measured up or down. It sits about 25 light-years away. You are not going to be asked to hold that number. You have spent the last 2 hours discovering, honestly and in detail, that holding it was never on offer to anyone. Not to you, not to the person who built the instrument that measured it, not to the man who named the unit it's expressed in, but there is a second operation available, quietly, underneath the first one, and it does not require comprehension. It only requires attention. The light entering your eye from Vega tonight left that star roughly 25 years ago. It has been in transit, unbroken, since before some of what fills your ordinary life existed. Whatever you were doing a quarter of a century ago, wherever you were living, whoever you had not yet met, none of it mattered to that light. Because light carries no memory of the journey and marks no passage of time along the way. At the speed it travels, the departure and the arrival are, from the photon's own vantage, not separated at all. The 25 years are entirely yours. They are the price your side of the universe paid for waiting, not a cost the light itself ever incurred. Vega is bright enough, and its light steady enough, that you do not need a clear countryside sky or a break in the clouds lasting more than a moment to catch it. A single gap between buildings, a single window facing the right direction, is usually enough. It is the plainest possible restatement of what a light year actually is, applied to a specific, nameable star on a specific night, a length measured in the only unit a human life is built to register at all. Think, for just a moment, about what has actually happened in the world during that crossing. 25 years ago, whatever argument or worry or ordinary Tuesday filled your attention has almost certainly dissolved from memory entirely, replaced by thousands of other Tuesdays since. People who matter enormously to you now may not yet have entered your life at all. 25 years ago, not even as a name. None of that history had the slightest effect on the photon in flight. It crossed the same vacuum at the same fixed rate, regardless of what was happening back at its point of origin. Indifferent to every argument, every election, every ordinary morning that filled the quarter century of its journey. Now follow it the rest of the way, because the last few centimeters are the most remarkable part of the whole story, and they happen inside you. That light crosses the vacuum for 25 years, entirely undisturbed, and then, in its last fraction of a second, passes through your cornea, bends through the lens behind it, and lands on the back of your eye. A chamber roughly the depth of a house key, sealed, dark, lined with cells built for exactly this purpose. Under a genuinely dark sky, a single one of those cells can respond to just a handful of photons arriving close together, which is close to the physical limit of what light detection can do at all. There is very little room left between what your retina already manages and what physics would allow in principle. There is no receptor anywhere in the human body for distance. None. There are receptors for pressure, for temperature, for the tilt of your head, for light itself. But nothing, anywhere in your nervous system, that measures how far away a source is. Every sense you have ever had of far and near has been inferred, calculated, and handed to you secondhand, assembled from cues. The angle of two eyes, the size of familiar things, the way nearer objects slide past farther ones, none of which survive the trip past a few dozen meters, let alone 25 light years. Inside each of those cells sits a light-sensitive pigment called rhodopsin, and it is worth naming directly, because the whole 25-year journey ends at this one specific molecule. A single photon striking it is enough to flip its shape. An extraordinarily fast, extraordinarily small event, over in a fraction of a millisecond, and that one shape change is the entire hinge on which 25 years of travel finally does something in the world. Nothing about the scale of the journey shows up in the size of the event that ends it. A quarter century of crossing empty space produces an effect smaller than anything you could see, even with the finest optical microscope, inside a cell you have never once consciously felt operating. What the eye actually reports, when that 25-year-old light finally lands, is simpler than distance. And, stranger, it reports arrival. Something is here. and it reports that arrival in the present tense, because the present tense is the only tense your nervous system has ever been able to speak in. A photon that left a nearby lamp 1/100th of a microsecond ago and a photon that left Vega 25 years ago arrive at the same organ, tagged with the identical word, now. That is the actual reason the unit had to be built from time in the first place. And it is worth returning to, once more, at the very end of the night. The body has no organ for distance, and an extraordinarily good one for duration. A pulse that has been counting since before you owned a watch. A year you have lived more than once, and can compare from the inside. When a quantity of space arrives too large to be held, the only place left to put it is the one dimension the body was actually built to register. Uhl did not choose a year because it made for elegant prose. He chose it because it was the only material on the shelf. There is a way to hear everything tonight as a kind of loss, and it is worth setting down plainly one last time before the night ends. 6 honest methods failed. A structural limit in your own mind was documented, named, and shown to apply everywhere a number gets large enough. Money, distance, brightness, duration. None of that was overturned by the end. If the measure of the evening were, did the light year finally become comprehensible, the honest answer would have to be no, delivered without qualification. But that was never a fair measure, and by now you know exactly why. Bessel did not comprehend 11 light years, and the number he produced was still correct, still useful, still the beginning of everything that followed. The engineers who built Gaia do not comprehend the distances in their own catalogue. And the catalogue is still, by any reasonable standard, one of the great achievements of instrumental science. Comprehension was never the thing standing between you and a working relationship with the universe. It was never required for anyone at any point in this specific story, and knowing that precisely is the actual outcome of tonight, worth far more than a trick that had pretended to succeed. You cannot comprehend a light year, and by now that sentence should carry no disappointment in it at all, because you understand exactly why it is true, and you understand that the finest instrument ever built, pointed by the most careful people who ever lived, has never once required comprehension either. What you have instead is smaller and, in its way, more remarkable. A real photon, timed by a real physical law, ending its 25-year crossing in a molecule inside your own eye, on an ordinary night, while your pulse keeps its own small, complete count of a duration you were always going to be able to hold. The universe will still be here when you wake up. So will we. Good night.